Today we're going to present one of our recent projects for analyzing and load rating a continuous post-tensioned precast girder, I-shaped girder bridges. And as Bid introduced, Dr. Manna Mahmoud is the other presenter, and both of us have been worked on this project together, and I was fortunate to be working with Mahmoud on this, and he will definitely share with you a lot of his experience from this project. And so just quickly to go through the bridge and the outline for this, we'll just talk about the bridge in general, and then the finite element modeling that we had to do the analyzing the bridge to determine the internal forces so we can do the load rating of the bridge. The first part is the bridge description. So as you can see, this is a two-span bridge, continuous. The total bridge length is approximately 280 feet. Each span is 140 feet, and we will describe later the two spans were made continuous together. So it's one continuous span, 280 feet. And the bridge is crossing an interstate system. So the bridge, the superstructure of the bridge is made of 5 precast girders spaced at approximately 9 feet, and the total bridge width is approximately 43 feet. And the deck slab is a 7-inch deck slab acting in composite action with the precast girders. Now, as I explained, the girders are ASHTO type 5 I-beams, which is 63 inches deep, the girder itself, and the girder is pre-tensioned with 14 bottom strands and 4 top strands, and the strands are 1/2-inch strands, grade 270. So those are the pre-tension girders, and that's mainly the pre-tension is provided during the construction of the girders and for during transportation and during erection, as we will see, but they are just mainly to carry the own weight of the girders or the beams. And then the beams are provided with post-tensioning, which is continuous and which is making the bridge entirely continuous together. And then the deck is made continuous by using closure pores or cast-in-place joints or wedge joints. Just a brief, the beams are I-shaped, but due to the continuity, you would expect, as you can see here in the middle part of the bridge, closer to the intermediate support, the beam is made as a solid section or a rectangular section, as you will see the reason for that, which is expected because that's a high negative moment area and it's a high shear zone area. And Mo will explain the details when you calculate the capacity of this section with the negative moment. Why do you need to make it rectangular? Because of the high tension force, and you need a high compression area for the concrete to resist the forces. So mainly the solid section or the solid part of the beam, and that is mainly made through that the beam itself is made rectangular and also having a closure pore at the intermediate support. Just to give you an idea that how the construction of the bridge and the sequence of the pre-tensioning and the post-tensioning is also impacting the analysis and how the bridge is designed. So the bridge, the span, the 140 feet span is made approximately of 2 segments. Each segment is approximately 70 feet. So the girders transported to the site is not the entire 140 feet span. It is basically 69 or 70 feet span. And then to do that, you will have to use an intermediate support or a temporary shoring between the 2 segments. This is the center line of the intermediate bend, and this is definitely the abutment. So from this center line of bend to the abutment, that's your 140 feet for the 140 feet. So you have 69 feet segment transported to the sites. They are already pre-tensioned with the 14 bottom strands and 4 top strands or 6 top strands. And then you have the PT, the post-tensioning ducts inserted inside the girders. Now, to make this span continuous, you have to have this 1.5 foot closure pour between the two segments is cast with the deck, and there is the other closure pour at the intermediate support. So basically the two spans are made of 4 segments, and the 4 segments are all made continuous by casting the deck with the closure pour. After you cast the deck and the closure pour and you reach a concrete strength of 5,000 psi, the post tensioning, the continuous post tensioning is applied, and definitely this is an approximate shape drawn in PowerPoint to show that the cables are draped cables, and definitely they are elevated once you get closer to the intermediate support, so the continuous post tensioning cables can produce moments opposite to the moment from the external forces or the applied forces on the bridge. So given this construction of the bridge, that is how will impact your analysis, and it will also impact your internal forces to determine the primary post tensioning forces and the secondary post tensioning forces, in addition to the moments from the external applied loads, either as dead loads or live loads. Now let's start the finite element modeling and how we utilize the staged construction feature, and that's the only way you have to do with the staged construction, due to the existence of the pre-tensioning strands in the precast segments, and then how the segments were made continuous together by the user of the closure pours, or some people call them wedge joints or cast in place joints, and then the continuous post tensioning. So the first stage, which is having the 4 segments, each segment is a simply supported segment, and for the segments to be in place, you have to have the temporary shoring or the temporary support at the closure pours. So you have one abutment at both ends, and then you have the intermediate bend, and then at mid-span of each of the 140-foot span length, you need a temporary shoring or support to be able to erect the precast segments. Definitely the pre-tension or the pre-stressing, generally, just also to make sure that terminology is clear, the word pre-stressing, it's supposed to mean either pre-tension or post-tension. It is generic, that is how it is, but in many states or in many practice, people refer to the pre-tension as pre-stressing only. So to avoid any confusion during this seminar, we adopted the word pre-tension and post-tension, since both of them shall fall under the umbrella of a pre-stressing forces. So the pre-tension force is applied at the stage 1, which is the simply supported segments. You can see in the model how the bottom strands were applied and the top strands were applied. So you will have moments in the beam from the own weight of the girders or the segments, and the moments due to the pre-tension force applied. Now the deck, the weight of the fresh concrete applied on the deck and the weight of the closure pours are acting on the simply supported beam segments, since they are acting in simple manner, and you can see the weight of the fresh concrete is applied to the simply supported segments. Once the deck is cast and hardened, you will have the deck acting in composite action with the beams. However, they are not continuous yet. So in other words, the moments due to the own weight or the fresh concrete of the deck is still acting on the simply supported. So the temporary shoring is still active at this stage. Then you move to the stage 4. Once you apply the post-tensioning force, now the temporary shoring or the intermediate support at the segments does not exist anymore, and that is simply you would expect because of the strands, the PT tendons, they are acting at the bottom part of the beam here, so the beam at the intermediate shoring will lift up, which is due to camber, and in this case you will expect that the beam is acting 2-span continuous, and the temporary shoring is definitely no longer needed, so you have to eliminate or remove the supports representing the temporary shoring at this stage while you are applying the post tensioning. Also to let you know, I mean, the post tensioning force was applied from both ends, so we had 2 live ends, and that's mainly to minimize the friction losses, since you have 2 live ends, and instead of applying the pre-stressing force from one end, which will have more losses due to friction. and also the anchorage slip. So now you have two live ends, and this was taken into consideration when we estimated the losses. So this is a stage 4 with the PET tendons. Now, just to let you know that to estimate the losses in the PT, since we have pre-tension and post-tension, so we had to use the refined estimates for the time-dependent losses according to the AASHTO. And just to give you an idea of the number, we estimated the PT losses to be approximately 22. It was exactly 22.3. But again, it was dependent on the location of the tendon. We have 3 tendons, but on average, it was 22%, just to give you an idea. And that's mainly because of the long span as well. So the friction was significant losses as expected for post-tension in general. Definitely, we are showing here a sample of the calculation. This was a tedious calculation that we carried out by hand. Due to the complexity and the importance of the bridge, we had to do everything by Midas and do everything also by in-house hand calculation. So we have to double check each other. Now, just to give you an idea, that is the actual cable profile, or that is the physical cable profile based on the eccentricities provided. That's the shape of the cable. As you expect that you will have higher eccentricity at midspan, and you have a smaller eccentricities at the intermediate support, and you will see the reason for doing that when we compare the actual or the physical cable profile and the effective cable profile. You see that this eccentricity increases significantly at the intermediate support, and that's the whole idea of having continuous post tensioning. Now, the stage after that was applying the barrier load on the top of the deck, and that's mainly applied to the continuous structure, and it's applied to the exterior beam since we are doing a refined analysis. So we'd like to maintain it as accurate as possible, and we applied as uniform load on top of the exterior beams. And then the post-construction phase, which means that you have the construction completed and the structure is ready for vehicular live load to apply the different live load. In this presentation, we will mainly focus on the HL93, which is the common truck or the design truck according to AASHTO, so the numbers are familiar to everybody without going into the different type of construction. And just to show you a sample that the maximum positive moment, which was approximately at midspan, we know that the maximum positive moment is slightly off the midspan due to the continuity. But as expected, that the case of loading that produce maximum positive moment in an exterior beam, you are loading one span with 2 lanes with multi-lane, and approximately the HL93 truck is acting at midspan. Now, when you try to find the location for the live load, you have to remember, according to the AASHTO, that to find the maximum negative or finding maximum reaction, you have to consider also loading 2 spans at the same time with 50 feet minimum distance between the 2 trucks, and also reduce the load by 90%. And this is also a feature that we utilized in Midas to be able to find the maximum negative moment for the exterior beam. And that is the loading position that produces the maximum negative moment in our exterior beam for the maximum negative and the intermediate support of the exterior beam. Now I'll move to the structure analysis, and then after that the load rating. And I think Dr. Manna, he is the one who's going to present this section and discuss the details with you. I'm sorry if I had to go a little bit fast, and that's mainly I wanted to stay on track with respect to time, to make sure that we are within the 1 hour. So now I will hand it over to Bid or Dr. Manna so he can present the remaining sections of the presentation.
Okay, Dr. Manna, you should have access to present now. Okay,
Can you
Dr.
see
Manna,
my screen?
we see your second screen.
Okay, let me see. Okay. Okay, can you see my screen now?
Now we can. Perfect.
Okay. Thank you, Dr. Hatem, and thank you everyone for being with us today. I'm so sorry for this technicality on the connection, and I will try to keep it in the 1 hour window and not go much more. As Dr. Hatem said, I will be talking about the 2 other stages, 2 other points of our presentation today. The structure analysis part. Basically, we are done with the finite element, and we are looking into the straining actions. After that, I will conduct the load rating based on LRFR. Also, the load rating we conducted was conducted by our in-house calculation or in-house spreadsheet, plus the Midas load rating module. Now I'm showing you the first stage, which is the bending moment. All the segments are simply supported and carry its own weight. So basically, WL squared over 8 will give you the moment for each of the segments. The next stage is actually we're still in the first stage. We have in that stage both the own weight of the segments plus the pre-stressing force or the pre-stressing effect coming from the pre-tensioned strand. We have 18 pre-tensioned strands, 14 at the bottom, and 4 strands at the top. As you can see here, the moment we are presenting the moment that exists on each segment by itself. We move forward for the stage number 2. On the stage number 2, in addition to the moment that's coming from the own weight, we have the fresh concrete or the weight of the concrete or cast in place concrete on each segment. That will increase your moment or the total dead load acting on each segment. If you recall, the stage number 3 made the model continuous composite girder, considering the concrete is already hardened, but in reality, the girder will not be continuous till we have the post-tensioned cable installed, and which will be able to resist the developed moment on the continuous beams. So stage 2, stage 3 doesn't have any loading. However, stage 4, we already applied the post-tensioning force. If you are working with a post-tensioned element, you have to tell yourself, is this a statically determinate or a statically indeterminate element? If it is a statically determinate element, the pre-stressing effect results from the eccentricity of the cable only, which is known as primary moment, which we are showing here. Basically, you multiply your tension force or the stressing or the post-tension force with the eccentricity of the cable. However, if the element is statically indeterminate, like the continuous beam that we have now, there will be additional moment called secondary moment comes from the indeterminacy of the system. Here we are showing the bending moment due to primary post-tension force on the top and the secondary moment coming from the indeterminacy effect. Both moments, if you sum them together, will give you the total moment due to the post-tensioning. If you want to find the effective cable profile, you just have to divide the total moment from the post-tensioning over the post-tensioning force, and you will get you the effective cable profile that we are showing here. Once we are finished with the construction stages, you can now remove as Dr. Hatem said, we removed the temporary supports as the closure joints, and the dead load would be acting on the continuous girders. I'm sorry. And we can see here the total moment and the total shear for the exterior beam. You can see here that the measure, we are expecting that the maximum positive moment will be not at the middle. It will be shifted towards the end support. Also, the negative bending moment will be at the maximum negative bending moment will locate at the center support, with a moment larger than the negative one, the positive one. As Dr. Hatem said, we will only run the HL93, which we are using for design, for the design. HL93 comes as a truck, 7.2 kip truck with a uniform load, which is 0.62 kip per feet. Midas can give you the envelope case, which will give you the maximum positive, the maximum moment at each location, based on locating the truck or the load to give you the maximum effect. As we are trying to do the load rating, we can conduct load rating at each section. But for us, we already know that the load rating, it will be governed by the minimum rating factor, which will locate at the critical section. So for a moment, we defined 3 sections. F1, which is the maximum positive, F1, which is the maximum positive, is the maximum positive bending moment location, while F2 is a section for the negative bending moment. This is F2. F3, we know that F3 has moments that is closer, kind of closer to F2. However, the section itself has a different configuration or different shape, which results in a different moment capacity. F2 has a much larger compression area at the bottom, while F3 has less because of the tapered section of the I shape. If you look at the table that we are showing here, you find F1, F2, F3, you find the moment comes for the exterior and interior beams. You'll find that F2 is minus 2,360, while F3, which is give you minus 1,533 for the live load effect. For the shear, the maximum reaction or the maximum shear force will be located at the middle support. If the distribution of the stirrups is the same throughout the girder, the governing section will be at the point where you have less web of your beam. So basically, we choose 2 sections, S1 and S2. S1 is located at the beginning of the tapered of the I shape, and S2 has similar shape as S1. However, S1 and S2 has different distribution of stirrups. S1 has 6 inches spacing, while S2 has 12-inch spacing. Now we go to the last part of our presentation, which is the load rating. On that part, I will conduct the load rating, as I said, based on the SDR mascot sheet that we developed here, and also I will do the load rating based on from Midas module. The purpose of conducting the load rating is to find the live load carrying capacity for the bridge, which will determine the ability of the bridge to carry the design live load. Or if the bridge needs to be posted for the legal load for the legal vehicles, we can know based on the rating factor or based on the rating of the bridge. The procedure is very simple. You just have to calculate the capacity of the section and calculate the demand from the dead load, subtracted from the capacity, and divided over the live load to give you the rating factor for that section, or based on your limit state. We conducted, as I said before, that we conducted the load rating based on the LR-FR procedure. I was according to the manual for bridge evaluation, and we have checked two limit states: service limit states, which includes the stresses at the extreme fiber of the section. Also, the strength was for the flexure and shear, the shear force. This table is showing the load factor for the dead load, the live load, and also for the pre-stressing effect is very important. If we are dealing with post-tensioning, we have, and especially in statically indeterminate post-tension, we have to know the pre-stressing effect, how to come to play into the section. If it's gonna be, you will include both primary and secondary, or you will include only the secondary, such as in a case where you are checking the strength limit state. Service 3, you have dead load was 1 load factor, and strength 1, 1.25. For the inventory or the design HL93, you will have 0.8 and 1.75. The pre-stressing is always 1. Now I will talk a little bit about the section design or the section analysis in terms of the capacity. We are trying to find the capacity of the section for F1, F2, and F3. The cable itself, or the cable profile, is different, or location is different from each section. F1 is very fortunate section. The cables are located at the top, at the bottom, and the lever arm is huge in terms of you have cables at the bottom, and you have a very wide flange on the top. That will give you a very high capacity compared to the other two sections. If you go to F2, you will find that the cables located still on the precast element, which will decrease your lever arm from the center of the cable to the compression part, which in this case will be at the bottom of the section. That will lead to a less capacity for the section, and also you will have a smaller strain at the cable location or the center of your cable. If you go to F3, it's much worse, because now you still have a smaller lever arm compared to F1. Also, the compression part is the bottom, but the compression area is not as wide as F2 or even for F1. So you will have the neutral axis will shift more towards the cable. That will give you a smaller lever arm, and also will give you a smaller strain at the location of your cables. As we said, we designed or conducted the load rating based on a spreadsheet that we developed in SDR, and I'm showing here the capacity of the maximum positive section F1. You can see here all the calculation was done, and the capacity was almost 12,500 cubic feet. Let's look at the capacity for each section. We used the H2 equation to calculate the capacity for each section, and also we use the strain compatibility method to get the strains for each to calculate the strain for the post-tensioned cables. As we expected, F1 has a very large capacity compared to the other F2 and F3. You find that the stress reduction factor is 1. That is based on the strain or the net strain on the cable is very large. You go to F2, you find that the nominal capacity is less. The strain was in the transition zone between a tension control section and compression control section with a stress reduction factor of 0.9. F3, as we expected, it's has a less lever arm and also has a less strain at the location of the post-tensioned cables, which or the net strain will govern as a compression controlled section with a phi factor of 0.75. So the FSC will control the load rating of this bridge in terms of the moment. S1 and S2, the shear capacity, we are dealing with a post-tensioned beam, so the duct will affect the stress distribution inside your web. And S2 takes this effect by subtracting half of the duct width from the effect from the width of the girder, and that was employed in our spreadsheet also to calculate the capacity for section S1 and S2. S1 we have a spacing of 6 inch, and S2 we have a spacing of 12 inch. We calculated the nominal shear capacity based on the general procedure to get the theta and beta for each section. I'm showing here only S1 with a 500 kip, almost 500 kip capacity. This is comparing S1 and S2. As expected, S2 is less. The step-up contribution is less in the nominal capacity, which leads to 369 compared to 500 kips for the S1. The load rating we calculated based on the equation that I provided before, and we calculated for all sections. I'm just presenting F1 and S1, and as you can see here, the strength is 2.3 and 2.98 for operating, and shear was 1.5, which is pretty good. Just a very quick on Midas load rating and design. On those locations, the idea was to compare our results that we have obtained from our in-house spreadsheet and the Midas results. All the numbers that you saw here have been verified based on a hand calculation and Midas, as Dr. Hatem said. So F1, F2, and F3 are located at those elements. In Midas, you just have to go ahead and choose the output or the design at those locations. On the tab, if you want to see the exact calculations, the stresses at the location of your strands, on the stresses, the capacity, all the detailed calculation that you already did by hand calculation or using the spreadsheet, you can go ahead and on Midas and go to the pre-stressed concrete design module and extract those results after, of course, you define the material, the parameters, and also the load case that you want, or the limit states base. I'm showing here the flexure for F1. You can see down here is 12,360, pretty much closer to our results. Also, I'm showing here the shear capacity on the right side. The rating, you can go ahead and click. If you have the module for the load rating, you can go ahead and choose to load rate the section or the element, and it will give you the output at the location where you are expecting. 2.28 is pretty good. We have 2.3. That's nice for the flexural load rating. For the shear, same thing. You can go ahead and conduct the rating on Midas at that location, and it will give you the almost the same. Will give you the same. Should be give you the same result as you have by hand calculation. With this one, I thank you all for your patience, and I am really sorry for that technicality in the beginning and a delay for starting.
Okay, thank you, Dr. Mahmoud. We're going to take a couple minutes to answer a few questions. There were quite a few that came in. So if Dr.
We can make it take 5 minutes, Bede, if you think. I mean, we can make it just 5 minutes or 10 minutes. I mean, it's up to the people if they want to stay or not, but we can take few questions, yeah, if you don't mind.
That would be perfect. That would be
Sure.
perfect. So if everyone is willing to kind of stick around for a couple minutes and
Sure.
answer a couple of the questions, we'll do so. If you do need to leave, we understand. Again, this session is recorded, so if you do want to go back, we will send you the follow-up link later on. Okay, to start off with the first question, it's why 6 pretensioning strands were used on top of the girder?
I mean, typically, with the pre-tension beams in general, you need to have all your pre-stressing is at the bottom. That's expected, but also you want to have top strands mainly for shrinkage, and during the stripping of the forms, if you don't have those top strands, there is always a tendency to see hair cracks and cracks on the top. So they are not really for strength purpose. It's mainly for serviceability. So you don't want to leave the top strand at the top of the beam without any pre-stressing for cracking and shrinkage.
Okay, thank you, Dr. Tam.
Yeah.
The second question is, can you please teach how to pre-stress losses is considered in the model?
Yeah, we did the calculation. I think Mo can elaborate on this, but in our model, we did all the losses, calculated them in the detailed method or the refined losses. We did that by our hand calculation, and we introduced the effective force in the model. The idea, this bridge has been in service for almost 30 or 40 years. So to do the losses in general, to do the time-dependent losses in Midas, you have to define time-dependent material properties, which will account for the shrinkage and the creep of the concrete as well. What we did, we calculated all our losses in detail, and we defined the effective force in the Midas model. Mahmoud, if you want to add something, but I know that's what we did, because we did the calculation detailed outside and introduced the effective force, because we are at service stage now. The bridge has been in service for 40 years already.
Yes, as Dr. Hatem said, we already did this one based on our calculations. However, if you want to do that, Midas has the ability to do the stress, the pre-stress losses for all the strands and also for the post-tensioning that you have. But as Dr. Hatem said, this one was in service for 40 years, and we just go ahead and applied the final or the effective post-tension and the post-tension and the pre-stressing force as effective. We did not do it in Midas based on the detailed output and define a time-dependent material. We did not do that one in Midas.
Yeah, go ahead, Bidia.
Okay, so the next question is, how did the removal of the temporary supports affect the dead load moment diagram?
Yeah, this is a very tricky question. It's not a tricky, you have to think about it. Before you remove the temporary support, you have simply supported segments. And even when you have cast the deck, there is no change in the bond condition. What happens once you apply the post-tensioning force? The post-tensioning force, since the cable at midspan is below the CG of the concrete, so it will push the beam up. That's why you have an upward moment. So the beam will camber upward, correct? So once the beam start cambering upward, what happens that the beam at midspan will leave the intermediate support. So basically your dead load moment will redistribute from a simply supported beam to a continuous beam. And this is when you see that now the dead load moment, even from the deck and the beam, will act on the new statical system. Once the beam is sitting on the temporary support, it will always act in a simply supported fashion segments. Once you put the pre-stressing force, that's the critical. You have to think deformation in this case. You don't think forces. Now the beam will camber upwards, which means the beam will leave the temporary support. So now the own weight or the dead load, whatever load you have, which is the beam and the deck, will act on the new statical system. So that's why when Mo was showing the moments for the total dead loads, you have the dead load now on the continuous, the two-span continuous beam. So basically, when you check the service stage, which you are checking now, we have to check due to the dead loads on the continuous structure.
Okay.
I mean, there is a lot of details. I mean, even the pre-tensioning, if you see the maximum positive section we showed, I mean, we don't have time definitely to go into the details, but this bridge has a lot of details. Like if you see the maximum positive section, it was at 62 feet from the support, which is almost at midspan. This simply means that your pre-tension strands are almost negligible when you come to calculate the section capacity at midspan, because it's very close to the closure pore. So the pre-tension strands are even still in the development phase. So you did not develop much stresses. Even if you calculate it as 6 feet, you start see that the contribution of the pre-tension strands. In addition, the pre-tension strands are only 14 strands. The PT, the post-tension, they are 66 strands. So just to give you an idea of the difference in magnitude of forces. So mainly the bridge is carried by the PT. And the other main point also, I don't want to go into detail. If you go to the effective cable profile, you will see that how much the secondary moment is helping you at the negative support. And it's not really helping you as much at the positive moment section. But I don't want to go much into detail, but that's precisely the effect of the continuity on the dead load moment.
Wow. Okay. Thank you. I think there's a lot of questions to the SDR staff. So I'm just going to ask one more question.
Sure.
And what I'm going to do is I'll share these questions with Dr. Tem and Dr. Reda Mahmood. So
Sure.
that way they could kind of address those questions a little bit more in their perspective. And when we have the review email that goes out and when they go to the page, you'll be able to see the questions and see the answer, the corresponding answers. So that way everyone's, you know, kind of curiosity is sated. Okay, so we'll just go into one last question down the list. The question comes in as, was there any issue with AASHTO service stress checks at the middle span while having top tendons continuous without debonding at the areas where they are not needed?
No, again, as I said, I mean, definitely the midspan section, there is no problem at all in the midspan section. I mean, that's even for service 3. I mean, the negative moment is always the issue with the continuous structure. The negative moments are much higher. So, I mean, we didn't show all the rating factors, but correct me if I remember, Mahmoud, even section F3 was the one that's controlling the rating, if I remember correctly. Section F1 at midspan was really the rating factor was 2.3 for service. And I think service 3 was definitely lower, but it wasn't the issue. I think it was always section F3 or F2 actually. No, F3, the one at the negative, when you have an I-shaped section. So the midspan was never an issue. Mahmoud, correct me if I'm wrong or if you want to add something.
Yes, you are correct.
Yeah, so I mean, the top strands, they're only 4 strands. They're not really doing nothing. I mean, you have the bottom strands, you have the 14 and the 66. So the top strand is not really, and the service was not an issue.
Okay, so again, Dr. Tem and Dr. Mahmood, thank you so much for your time today. Thank you for taking the time to address some of these questions and being able to present on your topic.
Sure.
Again, just letting you guys know, there is about another 16 questions that
Wow.
are
I mean,
ongoing.
I prefer to answer them in speaking rather than in writing. So would it be better? I mean, if we just, even if we end the seminar, if you can tell me the question and I answer them verbally, me and Mahmoud, while we're both here, and it will be recorded as part of the seminar.
I would typically say yes, but it's a lot. So we'll definitely conclude it off here today. But thank you
Okay.
so much. If there's anything else that we can do to, if there's any other questions that are coming in for the staff right now in the audience,
Sure.
please contact us right away and we'll be able to address them with Dr. Tem. If this becomes another thing where they have a significant amount of questions, it always leaves the room to be able to open up another session with Dr. Tem and Dr. Reda to be able to kind of discuss these questions and be able to formulate another opportunity to discuss it with the current audience. So
Okay.
that's always an opportunity. And to the people who are listening in, that's something that if you guys are interested in doing, please send in your questions and we'll be able to kind of make the decisions from that point on. Okay.
Sure.
Alrighty. Thank you
Sounds
guys so
good.
much for the. Thank you so much for your time today.
Thank you.
Before we end off, we have something called the Midas Expert Network that has been going on, and this is something that we have been focusing on in terms of developing a better community for the engineering staff. And actually, Dr. Hatem is actually one of the members. He's actually one of our expert influencers for the Midas Expert Network. So it's actually a community that we have been promoting that helps connect engineers in new innovative ways that provides opportunities for not just marketing themselves, like kind of what SDR has been doing, but themselves as an engineer, their companies, their opportunities, as well as potentially creating new business opportunities for the companies and the organization that they work for. So we do have a lot of government agencies as well as high profile companies who are linked with the network. So if there's any opportunities that you guys are looking for or looking to actually reach out or understand a little bit more about what the men can do, what the Midas Expert Network can do, please feel free to reach out. The website is very simple. It's midasoft.com/midas-expert-network. When you go there, you'll be able to kind of see a little bit more details and see some of the case studies that has been provided and some of the things that people have seen and how they were able to benefit from it. Because ultimately what we're looking to do is promote a better network so we can actually collaborate together as an engineering community and be able to allow engineers to market themselves and their capabilities as well as the company's capabilities with each other. So it's another step up than the social networking that you guys have been doing. And if for those who are interested in receiving this type of benefit, it's a very simple thing. You just need to sign up and fill in some questionnaires so that way you understand a little bit more about, we understand a little bit more about what you're looking for so we could connect you with the right people. However, if you're interested in being a contributor, an expert, kind of like Dr. Tem and Dr. Reda, you can actually visit a correlating page to be an influencer. And we have a list of influencers that are currently helping others as well to kind of reach out more on the technical level, guidance, answer various type of support questions, as well as more in detail in terms of answering more kind of like these type of webinars, QA/QC type. So we strongly suggest you guys to kind of take a look. And if you guys have any more questions, feel free to reach out and discuss with it a little bit more. So it's a great opportunity. And best of all, it's currently free. So yeah, please reach out and we'll love to kind of see where we can take it and take you guys. All right. But overall, thank you guys for participating in the session. We do apologize again for the delay and the technical difficulties and issues we had in the beginning, but hopefully you guys are able to learn upon the session today. We do have a follow-up session coming up in a couple of weeks with another engineer. His name is Dr. Anush Shamshabadi as well. So please look out for that email and that invitation. And other than that, please enjoy the rest of the day and the week, and please stay safe and healthy. Take care, guys.